Below them, one of Japan's fastest tidal currents was already pushing ships, barges, and suspended loads away from their intended line. At this height, even a small rise on the load gauge could force the entire lifting operation to stop. Before steel reached the sky, the Kurushima Kaikyo Strait was a maze of powerful currents, narrow channels, islands, and active shipping routes.
Engineers were not choosing the location of one bridge. They had to create a route across 3 separate waterways.
Their answer was a continuous chain of 3 suspension bridges, supported by 6 towers and 4 major anchorage positions. But every tower and anchorage faced different water, rock, and access conditions. So how could the crossing be built step by step? The current pulled every measuring cable downstream, so vessel position and instrument depth had to be corrected at the same time. Repeated survey lines revealed an irregular seabed shaped by scour channels, sediment pockets, and exposed areas of harder rock.
If you enjoy seeing engineering explained from the first measurement to the final structure, subscribe and continue the full process with us.
Surface measurements were not enough. Core drilling had to reveal what lay beneath the sediment at every critical foundation position.
By arranging each core in order, geologists could separate weak, fractured layers from the competent rock capable of carrying enormous loads.
Those results determined where steel caissons, concrete caissons, spread foundations, and deep anchorages would each be required.
Excavation began by removing the soft seabed material above each offshore foundation footprint, one controlled grab cycle at a time. As the tide strengthened, the dredger could drift away from its excavation grid unless tugboats and mooring winches corrected it immediately.
The pit deepened gradually, but each pass had to preserve the planned dimensions instead of simply removing as much material as possible. When the grab struck a rock high point, pulling harder would only overload the crane. The obstruction required a different tool. When wind and waves exceeded the working limit, the machinery was secured, and the crews waited rather than gambling with an unstable platform.
Only after repeated level checks confirmed the correct elevation could the prepared seabed be accepted for caisson placement.
The steel caissons began as enormous plate sections assembled around internal frames, strong enough to survive towing, sinking, and permanent loading.
Reinforced concrete caissons followed a different sequence, rising through repeated cycles of reinforcement, formwork, concrete placement, and curing.
Both caisson families progressed in stages, because sealing, internal stiffness, and dimensional control mattered as much as their final external shape.
Water tightness testing exposed even minor seepage before launch, while the structure was still accessible enough to repair safely.
Tow fittings, ballast valves, temporary lights, and monitoring systems then transformed the completed shell into a controllable floating structure.
Once afloat, ballast water and tug thrust had to restore level before the broad caisson could safely enter the open strait.
Wind and current acted from different directions, forcing each tug to change its pull without overloading the tow lines. When a rain squall closed the weather window, the convoy held position rather than continuing toward the foundation in reduced visibility. Ballasting increased the caisson's weight symmetrically, lowering it through the water while preserving level at every corner. As more of the shell became submerged, current pressure increased and pushed the caisson away from the optical reference line. Final seating occurred almost imperceptibly, with ballast adjustments distributing contact across the prepared bed instead of loading one corner. Tremie pipes were lowered into the water-filled cells, so concrete could be placed from the bottom without separating during free fall.
If pumping pressure climbed too quickly, the flow had to slow before the pipe blocked or lost its required embedment.
Deep shafts then extended the foundation into stronger material, while temporary supports, access systems, and drainage followed the excavation downward. Fractured rock introduced groundwater into the shaft, requiring pumping and localized sealing before excavation could continue safely. Mass concrete locked the anchor frame into the mountain, transferring future cable forces into an enormous volume of rock and concrete. Cooling pipes controlled heat generated during curing, because excessive temperature differences could produce cracks deep inside the anchorage.
Every major lift depended on hundreds of smaller decisions. Subscribe if you want to follow how the remaining structure rises above the strait. The lower tower block remained on the crane until guides, jacks, and survey instruments placed it accurately on its foundation.
A climbing crane then raised each new steel section beside the growing tower, where the wind became stronger with every level. The intermediate crossbeam had to enter both tower legs almost simultaneously, leaving only a narrow clearance at each connection. Permanent bolts and welds allowed the crossbeam to restrain the two tower legs before construction continued upward.
Each upper block was first guided by pins, then shifted by jacks until the splice faces aligned without impact.
The main cable saddle was one of the heaviest components lifted to the tower top, yet its groove orientation allowed almost no error.
The helicopter delivered only a lightweight pilot rope, which tower crews captured without entering the path of the moving line.
That pilot rope pulled a heavier hauling line, creating the first continuous connection between the two sides of the span.
Winches at both ends controlled the hauling line sag and kept it clear of tower steel as it crossed the channel.
Multiple support ropes were tensioned separately until their sag, spacing, and left-to-right balance matched the catwalk design.
The helicopter delivered only a lightweight pilot rope, which tower crews captured without entering the path of the moving line.
Even after completion, the narrow catwalk moved with the wind, demanding continuous lifelines and carefully controlled movement.
The permanent cable began with a single prefabricated parallel wire strand, pulled from its reel under tightly controlled tension.
At the tower top, rollers guided the strand into the correct saddle groove without twisting or damaging its bundled wires. The strand socket was connected at the far anchorage before the pulling load transferred gradually into the permanent anchor frame. Its sag could only be set after accounting for strand temperature, air temperature, and the exact mid-span elevation. When strand markings revealed a developing twist, the entire hauling operation stopped before the error became trapped inside the bundle. Radial hydraulic jacks squeezed the loose bundle evenly, transforming its layered shape into a compact, nearly circular main cable.
Engineers measured diameter, roundness, and sag before approving each compacted section for permanent cable band installation.
Each two-piece cable band closed around the cable at a surveyed location that would later carry a vertical hanger.
The first prefabricated hanger descended from the main cable, while taglines controlled its heavy lower socket in the wind.
As more hangers were installed, their changing lengths created the vertical support pattern required by the future deck profile.
Permanent bolts, welds, and internal connections finally turned the separate suspended sections into one continuous stiffening girder.
For the first time, all 3 suspension bridges and 6 towers stood connected, though commissioning work still continued across the system.